So you have part A, you have the Fourier transform, right? And you got part A, right? Did you get part A? Did you get part A? You are able to do part A. So the Fourier transform, so the function x is given by this 1 minus x over 2 absolute value, and this is only within x minus 2 to 2, right? And the Fourier transform that, assuming you just calculate it out, it should show that to be, Fourier transform for this function. But this is the Fourier transform of f, right? And the Parseval identity using the symmetric convention is that this f squared. And in this case, I mean, again, it's using this t is the transform variable. Minus infinity is just the original function square, right? That's the Parseval identity. Are you having trouble with this, or you don't know this is the Parseval identity? You know that, right? Parseval relation, whatever the name is. This in your textbook is derived using this convolution section. Let me point out to you the equation number that it's not written very explicitly. You can either use 20.74 and set f equals to g. Right? It doesn't have a standalone, or turn in the abstract form is 20.78 equation is just the same. Right? But explicitly it's like that. So for this is the right-hand side is just take this function and square it, and now you can restrict your limit to -2 to 2, and or you can actually do 0 to 2 because it's the absolute value. And this becomes symmetric, 0 to 2 and multiplied by 2, right? And this becomes 1 minus x over 2 square dx. And you know how to do this, right? So whatever that is, right? So you just integrate that out. And the left-hand side will be whatever that is, 2 over pi sine t, what is a pi? This will be a pi. Sine t over t square and 4 dt. Right? So whatever that is, you divide by this factor, would be the answer. Right? Is that okay? Did I answer your question? Okay. I mean, this is trivial. You just integrate it out and divide it by this factor. That should be your answer. That's the Parseval. That's what I try to point it out from the textbook. This section, the convolution section. The textbook derived that by using the convolution and divide the equation 20.74 with f and g, two functions, but you can always set f equals to g. You set f equals g, that exactly this equation. 20, this is from 20.74, right? If you like, I can rederive that using this Fourier transform. Is that okay? Rederive it again for you. Is that okay? Let me rederive this again for you using Fourier transform. Don't want to use on my time. I mean, do you know how to do it? That is just choice. So that equation is arbitrary for two functions f and g. And then the little f has the free. I mean, f. Let me look at which one is the transform of which one. One of them is the transform. So like little f is the transform of capital F. And little g is the transform of capital G. Then you can do that. Usually that involve complex conjugate. That will involve complex because the Fourier transform usually is complex. The original function may or may not be complex, but the transform is usually complex. Okay, and well, let's just do it big for because I mentioned a few times. I assume you know how to do it. Oh, we derive the Parseval identity using this Fourier transform definition. Now, like fx, you have fx, you get a transform, and you become capital. Let's just go back my usual notation instead of using a t. Is that okay? You have fx and Fourier transform this. So by definition, this is one of the using symmetric convention. That is just fx. And this is a transform, and okay, your textbook using a minus convention. It doesn't matter. It's just the same. Right? It's okay. So that is how you define the Fourier transform. Now you multiply fk and then f complex conjugate k dk, and you try to get what that is. Okay, and what you do is just substitute the definition of the Fourier transform into this one and that one, right? But when you do that, you need to be a little careful about the notation because you already use a k in this integration, right? And you just substitute this into that, and one of them is x, right? And then e to the I minus I kx and dx, right? So this one is going into this one. So, but then the next one is the complex conjugate. And you just take the complex conjugate in this and then put in here, but then you need to be careful about this. We cannot use the same x because you already use x in here, this integral, so this change to another variable, fx prime. When you take the complex conjugate, you're just changing the sign because this k is integrating along real f. K is real. You integrate along real k, right? So this becomes I, k, x prime, right? So it's just direct substitution. And I think that's all. Right? We have everything, dk, f complex conjugate. Yeah, no, that's complex conjugate. All right. And what you do now is integrate k first, because the only k dependency is this factor and that factor, right? So this exponential factor, that exponential factor, and combined, and so just write it here. So dk, you have the exponential factor I k x prime minus x, right? That's combining all the k dependencies. This one times this one times this one becomes this one. And you know this one, I asked so many times. Delta function, right? There's a 2 pi factor. X prime minus x, right? And then this 2 pi cancel with this 2 pi factor. Altogether is get rid of the k now. You only have 2 x integration. Get rid of all the exponential function. You have actually 2 integration. And then you have a delta function. X, right? And then you can integrate one of them out, like integrate the x prime out, right? And you use the delta function. And so everything, when you see x prime, it becomes x, right? So what is left is that x f complex conjugate x. Right? So yeah, that's the Parseval relation. It's okay. So you can be divided without using all these convolution thing. And just remember this. This is your friend. Remember this one. Whenever you have something like that give you a delta function which makes life easy. Okay. So remember that, and we divide that quite easily.